Hello, my name is Alan Tiao, and I am an undergraduate student at NYU. Today, I will be presenting our paper, What the Fork? Finding and Analyzing Malware in GitHub Forks. GitHub, as we all know, is the most popular code hosting platform with 73 million developers and more than 200 million repositories as of November 2021. As a result, we've started to see various ways the platform has been abused. An infamous example is the rise of threat actors that make malicious pull requests that introduce crypto miners to GitHub CI/CD environments, also known as actions. From a previous NDSS talk, we've seen how inadvertent secret leakage has become a problem that gives attackers opportunities to find tokens for unauthorized access quickly. We also see malware being served that ends up being part of the software supply chain, such as the Octopus scanner caught by GitHub Security Lab. Today, we want to present a new attack vector that has been slowly growing on the platform, which is the rise of malware that hides in GitHub Forks. We see that this is not an entirely new phenomenon, as an infamous case was the Electrum wallet, where malware forks were being used accidentally by other users that ended up stealing their cryptocurrency wallets. Such fork-based malware can wreak havoc in many different ways. One way is simply introducing backdoors into a fork, getting the developer to notice it in some way, such as through phishing or social engineering, and then having them use or merge the injected malicious changes. Of course, as noted with the previous article, another popular way is using forks as a storage solution. An attacker can store stages of malware in forks, have an initial payload compromise the victim, and pull from forks for further exploitation. Of course, this might be also nice for antivirus evasion, as GitHub might be listed as a trusted and benign network source. More popularly, we finally notice how attackers also use typo squatting or confusion techniques, where they would first name a malicious repository as something that might trick a user to see it as benign, and then wait for victims to accidentally misuse it and become infected. Now, one might say, okay, this is really similar to other sneaky techniques malware hides and propagates, such as maybe through file or blob storage or through an approved application store. So why is this particularly important? Well, for one, malicious forks are useful for stealthy propagation, where forks in their releases are generally not indexed by GitHub's code search capabilities. To make matters more complicated, compiled artifacts cannot be queried in a useful manner for security research. Such malware also has supply chain security implications, where employing such confusion techniques as described earlier can lead to users pulling the wrong and malicious repositories, which may end up being a dependency for another codebase. Finally, there is a lack of threat mitigations on the platform, as malicious repositories do require manual investigation and takedown. Now, this typically means that attacks have already occurred amongst users. As a result, let's talk about our research goals. We want to introduce fork integrity analysis as a viable technique for the detection of malicious artifacts in GitHub Forks. We want to analyze malicious behavior of fork malware we detect and present how they are being used and propagated against victims. With all the results we gather, we want to be able to make recommendations to better harden software delivery in GitHub's open source ecosystem. So when approaching this task, we initially took a look at 35 popular cryptocurrency repositories and being sure to not only include their forks, but also their transitive forks, so forks of forks. This yielded more than 68,000 fork repositories at the time of analysis. And the reason we aimed to look specifically at cryptocurrency repositories for our initial work was that we hypothesized a higher chance of fork abuse, given that there's a lot of monetary incentives often involved with proof of work cryptocurrency and their related illicit activities. So before running analysis on our target dataset of forks, we want to know how to identify one as malicious. And after examining some of the prior attacks that have occurred, we identified several criteria. The first being name typo squatting or confusion. Typo squatting is simply making minor edits to the name, such as those who accidentally make those mistakes will inadvertently use your software. Confusion, on the other hand, involves making less subtle changes and instead using names that might appear benign to users, which also ends up having a similar effect. Our work chooses to employ detection for typo squatting through the use of the Levenstein distance metric, while doing manual investigation into forks that might incorporate confusion, as it's not as straightforward to detect. Moving on, malicious forks can also be noted by the presence of malicious artifacts. This can exist in the Git tree/history itself, or as part of GitHub's artifact release feature, where precompiled binaries can be stored for distribution. Now, as one can imagine, this location does create a lot of risks for users. With this criteria, we now talk about how exactly we carry out our artifact analysis workflow, which looks something like this. We start off by gathering the artifacts from the fork repository we care about analyzing. We do filtering, which as we do limit our initial detection work to compiled malware, and then performing a similarity analysis to determine if propagated samples have already been seen. We do this with both a simple query of a hash checksum, and then also using locality-sensitive hashing with SSDeep, which looks something like this. Now, when ingesting a lot of samples, doing a linear search with a computed hash becomes really costly. Thus, we utilize a technique from Brian Wallace, where the search set is filtered by the hash's chunk size, which reduces the number of entries to check against. After finding similar samples, we also employ signature and capabilities analysis, which comprises of ClamAV and the Kappa frameworks, respectively. Signatures are really useful to help identify specific families or strains, while capabilities establish malware behaviors without more expensive dynamic tracing, which is typically and it's especially more useful for novel samples. Finally, alerts for malicious forks are all aggregated for our manual investigation and also to be consumed by repository maintainers. So given that analysis workflow, we then establish our overall detection architecture, which we dub Fork Sentry, which employs all of the heuristics that are needed to find a malicious fork. We designed this architecture to ensure that we are able to continuously monitor for new threats, while also being able to scale up for the large amount of forks, and to also be able to halt and resume execution when GitHub's rate limit is imposed on our analysis. So with this architecture designed and implemented, let's take a look at some of the analysis results in the time that we ran our study. We'd start by first examining how many malicious forks we ended up finding. And from our results, we discovered a total of 26, with 7 of them taken down by GitHub Trust Safety. This lack of insight on how takedowns are being validated and investigated makes it a little difficult to exactly understand our false positive rate at this time. From these, we noticed that crypto miners are high-value code bases, given the presence of malicious forks we found for them, and again reinforces how these threat actors will naturally gravitate their focus there. Next, we took a look at the actual suspicious indicators that were tagged for the samples we recovered. We noticed, again, strong presence of crypto miners, meaning that attackers seem to be more incentivized or inspired by the previous instances of abuse on the platform. We also noticed that there are the techniques of confusion do exist and are still used to potentially aggregate more victims quickly for mining. With these artifacts, we also looked at where they were typically found, which seemed to be nearly the same in both releases and the repository tree itself. We noticed that repository trees are often used as storage mediums for payloads, most likely those that are second stage, whereas releases are being used more in tandem with name confusion in order to serve malware directly to users through the platform. Looking at what operating systems these samples targeted, we noticed a strong presence of Linux malware, and that correlates really strongly with the illicit crypto mining behavior we noticed, and which, based on prior research, is oftentimes a lot more optimal because being able to mine on compromised servers is better than having it on a user host themselves. With these results, we also want to pinpoint some interesting case studies from some of the recovered fork malware that we have seen. One basic example is this a fork of this NiceHash repository, which we found to have employed typo squatting. We can see here that the minor edit between the initial organization name and the fact that, as previously mentioned, also serves its own pre-built releases. We also noticed an example of a threat actor that was much more persistent and sophisticated and served several samples that ended up also being very similar. We initially discovered them when taking a look at a repository called CPU Miner, where they were storing compiled binaries in the repository tree through direct upload. In addition, a transitive fork was also found, which also had compiled binaries as well. And when we saw the repository, we ended up doing a little bit more investigation into these accounts themselves. And we noticed a separate repository which was pulling down these binaries from the forks and then creating a systemd service that launched the binaries in a very suspicious way, and such that it would be launched every time the system is running on is rebooted again. We noticed from our detection results that the binaries itself were not only detected as crypto miners, but also with some interesting elf packing. Thus, we took one of the samples, and when reverse engineering it, it became noticeable that such a behavior was present, where another binary was encoded and stored to be unpacked on disk. And when this is dropped, we noticed that this was a shared object library that seemed to employ some form of initialization and potential anti-analysis through the LD preload environment variable. Thus, we established this workflow of what these samples were doing, and where it initially drops both an actual miner and an shared object helper, and takes the base64 configuration passed initially to become actual flags passed to the miner. This yielded a really interesting address, and we used that to check against the Ethereum network, which we saw not only a lot of routine transactions associated with the mining pool, but we also yielded quite a lot of profit from such activities, which ended up around $285,000 in the wallet. Of course, we do want to add a caveat, which is that we are not quite sure whether or not this is all from illicit crypto mining, but that really leads us to our key takeaway, which is that threat actors, some persistent, are taking advantage of lack of monitoring in forks to serve quite sophisticated malware. And there is ultimately a lack of security mitigation and awareness surrounding the proliferation of such threats. So we wanted to pose a question of whether or not GitHub has a responsibility to automate the detection of such malicious forks or delegate that responsibility to maintainers and security research like us. We believe that the answer to this is that they should, given that there is a strong implicit trust that users naturally place on the platform and the pervasive effects of attacks when exploited by threat actors. Thus, we make several recommendations to GitHub. First, we believe that some degree of typo squatting detection should be enforced to stop attackers from naming themselves similarly to critical accounts. Second, given the wide data sets of malware available, we believe the platform should employ scanning against uploaded artifacts. To complement that, better indexing and search should be incorporated, such as for forks and compiled binaries, which can vastly improve data analysis and security research efforts. Finally, we observed that GitHub releases do not really recognize the provenance of artifacts being shipped, as maintainers can upload any asset that they choose to their releases. We believe that removing this and enforcing maintainers to have a system that ensures transparent and reproducible builds mitigates away the threats of malware being stored in both their own repositories and subsequent forks. We also want to talk about some of the future work in this area as we aim to continue our research. One big area is expanding our analysis to incorporate source code and compilation manifest changes. This involves incorporating tooling that can enable data flow analysis to recognize adversarial capabilities. Our work can also benefit from really improved similarity analysis, where rather than determining similarity from a sliding window-based algorithm like SSD, utilize heuristics that are much more structured and context-aware, such as through their control flow graphs. Finally, simply expanding our data scope to encompass a lot more repositories, such as with BigQuery's GitHub dataset, which we hope can yield a lot more diverse samples to examine, while also giving us more insight about such threats in the open source ecosystem. Thank you for coming to our talk, and please let us know if you have any questions or concerns.